right, we're going to get started. Welcome everyone to our session, which we're really fortunate to be having a crossover session with the TROPOMI-OMI meeting, so that even though unfortunately we couldn't be at both meetings, we at least can have this session together. And so our focus, the title of our session here is 20 years of NO2 applications from OMI and TROPOMI. And we have a fantastic line of speakers here. And it's my pleasure to introduce our first speaker, Ellen Burkhard from NYSERDA, the New York State Energy, I should know this by now, New York State Energy Research and Development Authority. Thank you.
That's why we call it NYSERDA. Thank you, Arlene, and thank you, Jenny, for inviting me, and Tracy as well. A number of the points that I was hoping to make were made this morning, so this should be easy. But what I wanted to do is give you a little food for thought and maybe think about things in terms of an energy context. We're doing a lot of science. We're looking at air quality, talking to air quality agencies, thinking about public health, exposure, and what does that mean? But we're about to embark on a massive transition of our economy to decarbonize it. And so that's great because we're going to see change, and we like to see change on our graphs and everything else. So I am with NYSERDA, and I manage a portfolio of air quality and health effects research, looking at research that will hopefully help us make better energy decisions and also track how we're doing over time. A lot of accountability, and also build capacity in the state for doing this type of research so that we have informed decision-making. And this is an example of accountability. It's not TROPOMI or OMI or even tempo, but this is sulfur dioxide data. And I just wanted to show you in terms of how we think about changes, the transitions we're going through in the energy markets and regulation. So we've seen a lot of reduction in pollution in the Northeast. We've seen a lot of upwind come offline, of power production, and with that sulfur dioxide. So this is the upper left are sulfur dioxide emissions, and you see that go down dramatically over the last 20 years. And the text, which you probably can't read, are different regulations and also market drivers. So the low sulfur fuels for transportation, both on-road and non-road, were very important. Clean air interstate rule, cross-state air pollution rule, all very important. We also had this major recession. Many of us remember. And at that time, hydrofracking was coming on with natural gas and resulting in lower cost natural gas. And as the economy responded, a lot of that coal-fired production was repowered with natural gas. And so you see these lower sulfur dioxide emissions. In New York State and also our neighboring states, we put into regulation ultra-low sulfur heating oil for the #2 product. It's the same as is used in on-road diesel and non-road diesel. So it's all one product, and it's very convenient. And then in New York City, they phased out #6 heating oil. #6 is a very heavy oil. It requires being warmed up to flow. That's how heavy it is. And it's very high in sulfur. And as they took that offline, you can see in the lower right, all of these summing up to see this large reduction in sulfur dioxide concentrations in New York City. The modeling work for the health benefit on that phase out of #6 oil was to avoid about 300 deaths per year. So this is quite significant. And we like to think in terms of air quality. We like to think in terms of public health, the co-benefits to these energy changes. And in New York, you know, until recently, we were kind of driven by, in our department, thinking about the Clean Air Act, thinking about public health, because we have a health across all policies requirement in New York. But in 2019, they passed the Climate Leadership and Community Protection Act. And so this is a big reduction in greenhouse gas, massive reductions, the goals of 40% in 2030 and 85% reduction by 2050. But also to look at community health. And so how are we going to get there? We had a large scoping session over a year with all kinds of experts and agency heads. And so we're going to have 6,000 megawatts of distributed solar, okay, by 2025. We've been doing this for a couple of decades now. In 2026, it'll be fossil systems in new construction buildings will be prohibited. So think about heating systems now being electrified, air source heat pumps that are really coming on strong in the market. And now there's more sales of air source heat pumps nationwide than there are natural gas furnaces. By 2030, 70% of electricity generation will be from renewable energy. We're currently at about 28% in New York. There'll be 3,000 megawatts of energy storage, and we'll need this because of the intermittency of offshore wind or terrestrial wind and solar. And in 2035, we and many other states will be doing a lot of offshore wind. Construction's occurring now. We have the first turbines sending electricity in, and there'll be 9,000 megawatts by 2035. And our passenger cars and trucks will need to be zero emissions. And again, other states are doing this, and you know, there are some folks from California leading the way on that, Jesse. And then by 2040, we're going to be 100% carbon neutral in terms of our electricity generation. And then 2045, the medium and heavy duty truck sales have to be electric as well, zero emission. So that just kind of gives you a sense that there's going to be a lot of change. And I wanted to show an example of the offshore wind. And we have large goals in New York, 9,000, but we're not alone. All of the states in the region, Massachusetts, where we are now, have large goals. And you can see the different leases, areas where that offshore wind will be built. And there's this very small little project that's now, it's South Fork Wind. It's only 13 turbines, but that zero electricity electrons, they're flowing into the east end of New York, New York's Long Island, and that's enough electricity annually to power 70,000 homes. So that's just the beginning. It's only 130 megawatts compared to the 9,000 that we're going to be constructing. And so you can think about, well, what's that going to back off? And those other goals we saw at the same time, we're going to do a lot more electrification. So our load will grow, but we're going to be going over to zero emissions. And then since this panel was about TROPOMI and NO2, I asked Paul Miller of NESCOM, what can I say? And he shared this slide with me. This is Tao et al. Several of the authors are here, and some work that they did a few years ago. And we talked about this approach this morning as well. And they looked at the TROPOMI data for formaldehyde and NO2 and the ratio of those on low ozone days and high ozone days. And you can see that you've got I can't really see on this one. You've got NOx saturated conditions in the core, urban core, and NOx limited outside of that. And on the exceedance data, there was high formaldehyde, high NO2. And some of this may have a common driver. They were hotter temperatures. Hotter temperatures usually lead to more air conditioning, leads to more fossil generated electricity production, higher temperature, more biogenic VOCs, possibly the reason behind the higher formaldehyde. And the lower two figures are CMAQ modeling that Alex Karambellis did. Very similar patterns, although there are some differences. And I would say the take-home message here is that they are a little different, and that while there's some areas of that we could use this type of an approach to have strategies for improving air quality by reducing VOCs in the urban core, overall NOx reductions can be very beneficial, especially downwind. And then the final slide, I wanted to show another example and emphasize the community protection aspect of the Climate Act that we have. On the right is, well, this slide was given to me by Fred Moshari at City University, and he emphasized this is preliminary. So they're still working out a lot with the tempo data, but you see the pattern is similar between TROPOMI and tempo for August 22nd last year at about the same time. And so we have different patterns in different neighborhood scale, geographical areas. So we have spatial variation, and we can really look into that. But with tempo, we're also going to have temporal variation. And so that might be really important for how we look at exposure for community groups, because ultimately the benefits of doing all of this, it's not just climate, There's huge co-benefits in reduced air pollution, lower exposure, and improved public health. And someone showed PM globally in the trillions of dollars, and in New York, it will be in the billions of dollars. So with that, I guess I'll just finish up and say, you know, this is just a little food for thought, thinking about the energy market dynamics as we go forward over, you know, the next couple of decades, and how much change that will cause and where that change will occur. Thanks.
Thank you so much, Ellen. I just want to remind everyone that we'll do questions at the end. We'll ask all of our speakers to come up for a panel, and we should have about a half hour or so for discussion. So our next speaker is Bryan Duncan. Oh, did I click on the wrong thing? Okay.
Yeah. Yes, I promise you, I did not make any of these graphics.
Yeah, we use this animation.
Yeah. Okay, so I'm supposed to be in 2 meetings at once, at the OMI TROPOMI meeting and the HAQAST meeting. So this is the best of both worlds. I can be at both at the same time, and check boxes there. So let me just, can I go back one? Yeah. Okay. So this is the crossover session. And so here I'm going to wear both of my hats, my ORA Project Science hat, and also some things I learned about being in HAQAST from the very beginning, HAQAST 1 to the present. And for those of you who are new here, and I'm not speaking to the OMI TROPOMI folks here, so OMI is the ozone monitoring instrument. It measures NO2 and other species, and it's been instrumental in HAQAST for 20 years now. And let me figure out if I can go forward. And OMI is a contribution from the Netherlands and Finland to the ORA mission, the NASA ORA mission. Okay, so here we have this graphic that many of you have seen before. And so I'm just starting the animation. The years are in the lower left. And what I've always said about ORA is it was launched at exactly the right time to witness profound changes in air quality around the world. And this is just the US. And yes, okay, well, the air quality in the US isn't quite as clean as this image makes it out to be. It's there's a lot with color bars here, but that doesn't diminish the fact that OMI was there to witness decreases in urban areas of NO2 of 40%, 50% and more. Okay, and I have to say that the day President Obama, I think this is back in 2015, started talking about ORA OMI data, I was doing backflips for weeks because of that, and I still like to brag about it because it's not just the pretty pictures; it's the fact that the data are actually used in science. They're quantitative as well as pretty pictures. And this we've been supplying, when I say we, I mean the OMI team, has been supplying these images to EPA for years now, and they're in their air trends reports. Okay, so OMI is not done yet. It's still going strong after 20 years. But of course, we have ESA's TROPOMI and NASA's TEMPO now out there. They're newer, sexier instruments. But OMI has a very long, stable record, and it's still useful for many things and for the health and air quality communities. And I will point out that 2023 had the largest number of publications. And I would like to thank COVID, because I don't know if you saw in the news, there were a lot of images showing air pollution changes around the world associated with COVID. And OMI data really was a star for that in many respects. And that resulted in what I call the COVID bump, where there are a lot of publications that came out because of COVID. And there's still, people are still publishing with the OMI data record. And the reason is, and this is another animation, I'm going to explain it first before I start it. It's slow. But the reason why the OMI data were so important for COVID is that you were able to look at the changes in COVID in 2020, in NO2 in 2020, and put it into context of the envelope of meteorological variability. So NO2 varies a lot because of just weather variations. And so we have this long record, this long stable record, and we are able to see that this decrease in NO2 or air pollution because of the COVID lockdowns was statistically sound, was very a robust result. So let me start this image, this animation, and it starts March 20th to I think May 25th. I can't see the whole screen here. And it's an annual average, so it's a 2-month average for each year. And the year is I think in the lower right. Yes, so let me start. This is kind of slow, but you'll see a lot of the meteorological variability in NO2. So this is it, okay, 2017, 2018, 2019, lots of variability from year to year, and then 2020. So this was clearly something that was a robust result. And what's interesting is you can see that that even though there is meteorological variability, there is a noticeable decrease after COVID. Maybe it's because I work from home now. Okay, so one thing I wanted just to point out here is at NASA, when the satellite's aging and it's still doing pretty good, we say it's aging gracefully. Okay, so you'll notice in this final image that graceful part of it. There's some it's called striping. And you can always ask any of the retrieval folks about the details, but they're trying to account for this now. Okay, so it is aging gracefully, and hopefully we'll have 2 more years of satellite observations from OMI. And I have to point out that the engineers who built OMI and the Aura satellite and all the other instruments that from different agencies. This is just a testament to the overachieving engineers. They do an excellent job. And these satellites, even though these instruments and satellites were supposed to last 5 years, their design life, 20 years later, they're still up there. Okay, so, OMI data are still instrumental in supporting quite a few applications. They're still used here in HAQAST. And including, I wrote here as one of the bullets, validation of new satellite instruments. Maybe validation isn't the right word. It's more, cross-evaluation or something like that. But there's still life in OMI, and it's still definitely useful. In fact, it just popped up in the global burden of disease report that came out last month, and our very own Susan Annenberg's involved in that. And she was instrumental in getting NO2 into that report from OMI. Okay, so I want to take you way back to HAQAST 1. And the purpose of this slide, well, there's a couple of reasons. I just want to show you that these retrievals are a lot of work, and they just don't happen. They take a lot of effort by a lot of people over a lot of years. And for OMI, this has been 2 decades, and the retrieval folks are still working on NO2. But back in HAQAST 1, when I was here supposed to help facilitate the use of satellite data by the air quality community, I wasn't even convinced that what we were seeing from the satellite represented anything on the ground. I knew that there was pretty pictures and things like that, but qualitatively, I wasn't convinced. And then one of our retrieval folks, Lach Lamsaw, who's the brains behind a lot of these NO2 from OMI, he showed me this plot, and I think it was this very plot in about 2014. He said, "Now do you believe it?" And I said, "Okay, we're on our way." The NASA satellite variation and trends are comparing quite well to the EPA surface data in Houston, Texas. Okay, now putting my Aura hat back on. I just wanted to point out that OMI has contributed more than just NO2 to applied sciences at NASA. A lot of people forget about the stratospheric ozone layer, the ozone hole. OMI has been integral in that monitoring effort over the last, 50 years, 60 years now? 50 years, I think. So don't forget that. That was one of the greatest application successes of satellite data that guided international policy decisions. And so I'm almost done here. So this is another graphic of SO2. And this, again, that's another animation. And again, right place, right time. And OMI witnessed an incredible reduction in SO2 associated with efforts to remove SO2 pollution from thermal power plants in the US. Hopefully we have 2 more years of operations. We have at least 1, but budget constraints may keep us to 1. But I think we made a strong argument to continue for another year. So hopefully we'll have 2 more years. And the date that end of science will occur for OMI is scheduled as May 27th, 2026. So I'll just leave this up. There are plenty of resources where you can find out more for all the new people here. Wonderful graphics and animations and information for you. And I also included my name at the bottom. I'm a resource. I always answer emails. So if you have any question, please reach out. I don't care if you think it's a dumb question, just ask. Okay, thank you.
Thank you, Bryan. Our next speaker is Michael Geigert from, I think so, yes, from Connecticut's Department of Energy and Environmental Protection.
Okay, so we tap on the up button, the next button, the right button. Okay, so anyway, thank you for inviting me. Many of you know me, but there are some new faces here, so we'll give a brief introduction. Anyway, out in Connecticut, which isn't too far away, we do have issues with ozone. And we're not the only ones. We go hand in hand with Texas, Chicago, LA. But we're the last holdout really on the East Coast. It used to be Maryland, the big hitter for ozone decades ago. But for some reason, their control strategies worked a lot better than the ones around our region. So we're still struggling. But what you're seeing here is the decline in our design values for ozone. And that's what really counts with EPA, right? Design values. You have to see the bottom line there, the latest standard of 70 ppbs. We have 2 areas, non-attainment areas. The top one, the red one, is Southwest Connecticut, New York, and New Jersey. It's kind of flat. And you can see at the very end there, it went up. 2023, you might guess why it went up, because we had smoke. And because of that, we are submitting an exceptional event demonstration. It's a real uphill battle, just like the uphill battle with the design values for these. Greater Connecticut was heading down. We thought it might have hit the standard this year, but it went up too. So we're going to concentrate on those monitors. Anyway, so here we go. For the very few of you that don't know where Connecticut is, right? There it is. The design values are the highest along our coast. We have 82s. And I was told by Texas that we might have beat out Texas. So congratulations there. But you can see Greater Connecticut. I live actually in Abington. I have a monitor very close to my home there. But our design value is just above 70 and Groton went up. So basically, that's what we have to deal with as a state regulator, is finding ways to get our ozone below the standard. Okay, so this is an homage to Bryan Duncan, right? In the beginning, there was aura. There was actually GOM, but we never used it because the resolution was never that good. So aura, you know, had a OMI actually had, it was 13 by 24 kilometers, right? You know, TROPOMI surpasses that, and so does Tempo. So, but OMI has done a good job over the years, and it was launched 2004, and it was part of the A train. Do you folks remember the A train? We used to always talk about the A train, right? And basically the A train would just, it had the MODIS. And that's really what I did to start the forecasting early 2000s. When MODIS was revolutionary, right? Do the fires and everything. And so basically the A train really set the standard. And it wasn't really till TROPOMI till we really saw improvement in resolution. But I want to show this. You got to see this with Bryan. the 2005 to 2022 NO2. I just want to prove to you it is related to ozone, right? You put these two together, you do the fourth highs, it's what we use for our design values. On the left, 2005, basically the whole Northeast had orange, between maybe 80, 90 ppb fourth highs, so in exceedance. I haven't done the 2022, but you could see on 2021, just a few blotches of orange in Connecticut. So the control strategies have worked. We're just above the standard, but you definitely have to deal with it. So what's going on with those? Okay, as you said, the power plants were the big thing, right? The SO2 went down, the NO2. So this just in our area, but the power plants eventually, and the emissions came down in Pennsylvania and Ohio too. But they're still the real big producers compared to us. Look at Connecticut. Connecticut's almost flat line there. You can barely notice it on the chart, right? For EGUs, we just hardly produce anything. And New York, this is the whole state of New York. They have big generation to our west. Probably a good chunk of this might be New York City. So anyway, it's been going down. So EGUs are sort of the big issue. Well, not as big an issue, mobile sources. We all know that from the NEI, right? Mobile source is more than 50% of the NO2 now. So everybody wants to electrify the vehicles. So what is going on? So anyway, I just wanted to show this. You might have seen this illustration. Folks on the OMI session would certainly see this. We got all excited when we saw this, the OMI versus TROPOMI, and now tempo would be even less than that. So it was a major advancement, and it actually, the resolution went down to 5.5 kilometers by 3.5 because it was originally at 7. So basically, we're going to show you some TROPOMI here. And Dan Goldberg's going to show you a lot more. Okay, now I have this on for a animation, and I might have to click it again because on the slide itself, yep, there it is. There, right? It's hard to see where it's going here. Oh, okay. Didn't do it? Okay. The cursor is very hard without a mouse. It kind of disappears. See if you can get it. Oh, two-handed. If it did work, you would see, yeah. It says cannot play media. That's typical on a Apple, right, on a Mac. I mean, it really is. Okay, if you, because I don't save it as the proper format, but if you saw this, okay, 2018, of course, 2020, it goes down as you showed, then it kind of goes back up again by 2023, not as much as 2018. So we're definitely still going down. And let's see. Okay, so here, so what is the issue with New York City? Is it the mobile sources or is it the EGUs? Now see the concentrations. Those are power plants, basically. I kind of scaled them according to their mass tons, the ozone season. You're not seeing, this is the TROPOMI column for the summer, but you're still seeing a lot of power plants in New York City. A lot of them are going to be decommissioned and definitely going to see improvement. But what is it just those units? What is really causing this NO2? Because this NO2 bubble is the NOx saturation that we have to deal with. Okay, so, and then we had tempo. I had an animation here, and I'm fearing it probably won't work either. But I wanted to show you for May 24th. Look at that ozone event. When we see this, a lot of times we're suspect why there's such elevated ozone. There was a lot of smoke last month from Mexico being blown up. You can see the visible smoke plume. HMS had it. And this would have been an animation if it wasn't a Mac, but let's see. Let's see if I can get that. Look at that. Does it say cannot play? Okay, well, what you would see, basically, I didn't, there were some clouds in the morning. I didn't filter it for clouds. I filtered it for the QA factors. Tempo has how many minutes? 2 minutes. Okay, so maybe on your own home computer this will work. But basically, that may have been cloud residue. But during the day, what you're going to see is it kind of just concentrated around New York City. So, but the resolution was quite good. And so, no animation there. So I was able to do this. So you will see the tempo. That's tempo on the right, TROPOMI on the left. Kind of scale them. So I was pleased. It was pretty similar, but we still had that blob. That could have been clouds over Maryland. But anyway, that's Connecticut area, New York City. And I promised this to Laura Judd, because this is what we need. Satellites, 250-meter resolution. What do you think, 20 years, you'd be able to do that? That's what we need. Because this way, if you look at the 3 runs she did, okay, you've got 14Z, 17Z, 20Z. I outlined the airports and some of the power plants. You can see the plumes coming off. On the left there, see the ship dock? We're wondering if a cruise ship or something was there or something. I don't know, but it was pretty interesting. You're seeing these NO2 areas in places you might not expect, but power plants definitely, airports. So anyway, that's the vision for the future. And thank you for helping us regulators out all these years tracking air pollution. Okay.
Thanks so much, Michael. Our final speaker in our panel is Dan Goldberg from GW.
Yeah, sorry, Michael. I developed these on a Mac, so I guess that's why they're still working. Yeah, thank you all for having me. Thank you to the OMI TROPOMI meeting for doing this joint session. First of all, I'm just showing some eye candy of TROPOMI NO2 globally. I discussed how this data will hopefully be publicly available on the Earth Data website, gridded. But it's just very interesting to see the seasonal cycle, the monthly cycle of TROPOMI. Today, I'm going to be focusing mostly on urban scales. So this is the only global image of the day. But before I get started, I want to thank all my co-authors. This is actually just a fraction of them. A lot of work, including all the OMI and TROPOMI science team delivering an amazing algorithm for NO2, which is what I'm going to be focusing on today. And also thank you to the funding, NASA HAQAST, NASA ACMAP, and the AQRP. All right, so maybe I should have opened this slide at the beginning of this session, but this is a nice little comparison Venn diagram between OMI and TROPOMI. Let's start where they're similar. Both measure column NO2, both measure formaldehyde, ozone, and the algorithms are very similar. Caroline already mentioned this in the tempo. Retrieval is also very similar. But where it's different between tempo and OMI and TROPOMI is that they're polar orbiting. They take a measurement once per day, about 1:30 in the afternoon, and OMI and TROPOMI are approximately that same time. Where they are different is really in the age. OMI is almost 20 years old now. TROPOMI is almost 7 years old now. The spatial resolution of OMI is relatively coarse, at least in today's age. And also one other thing is that it's pretty coarse at the swath edge, whereas TROPOMI has this very fine spatial resolution at the center, but also at the swath edge as well. You know, TROPOMI is a newer instrument, has a little better signal to noise ratio, uncertainty of the measurements a little bit better. So therefore, it's generally better for urban scale studies, for short time scale studies, and better for recent trends. However, OMI is definitely the one if you want to look at data before 2018 because it has the record back to 2005. And also one thing that wasn't explicitly mentioned, but the OMI does have this row anomaly. So half the data is missing. We wonder what it would have been if we didn't have that row anomaly. It would have been even more amazing. Bryan Duncan showed this at the national level. Now I'm zooming into the urban scale, showing the changes in NO2 amongst 4 cities. I put a few more in the supplemental. If we have time, I can show it, or you can download it later. But we've seen drops of 50 to 60% in most US cities. Houston is kind of the outlier here in this particular example, but really dramatic drops in NO2 over, this is showing 16 years. We've actually done this work over the entire world, and I'm just going to mostly reference this paper, this 2021 ERL paper, but just to show that OMI generally matches the emissions inventory trends in the United States, but elsewhere globally, there are some varying trends between the emissions inventories and OMI. OMI is the black line, the various colors are emissions inventories. So OMI is helpful in the US, but I think OMI and TROPOMI are especially helpful globally, where they have many fewer monitors on the ground to monitor NO2. So now doing a more direct comparison between OMI and TROPOMI at the urban scale, and we can see that generally TROPOMI can capture the spatial heterogeneities within cities a little bit better. I think this shows best up in the Washington, DC and Atlanta cases, but even still Los Angeles and Houston. We can very clearly see the difference in extra spatial resolution, what that gets us when we use TROPOMI versus OMI. This is an overlapping year, 2021 annual average. And again, I have more images supplemental, happy to discuss that later. One paper that was recently published a few months ago now, we compared TROPOMI directly to the emissions inventories. This particular paper wasn't looking at the magnitude, but instead at the spatial agreement between the two. And we can see New York City, Houston, we're seeing really excellent agreement in the spatial correlation between the emissions, which is on the left, and the actual TROPOMI NO2 on the right. There are some exceptions. One of them is near warehouses, and Geigert has a paper that was just accepted on this. He also discussed this at the last HAQAST meeting, as well as in EJ locations. And again, we have some work on that as well, which I don't have time to talk about right now. But one thing I do want to focus on in this particular, most of the rest of my talk, is using TROPOMI to estimate the surface concentrations. This is showing a simple linear fit between TROPOMI and the EPA HAQAST NO2 measurements. And I know that this might be good for this audience, maybe the TROPOMI audience might scoff a little bit here, but a very, very rough heuristic to convert this column measurements in surface concentrations is simply to multiply by a factor of 2 times 10 to the negative 15. So if you're seeing a TROPOMI or tempo value of somewhere around 5 times 10 to the 15, very, very roughly, it's somewhere around 10 parts per billion. Again, this is just to give you a very rough heuristic of what these mean at the surface concentrations. But also what I want to point out here is that the correlation, just this simple linear correlation, shows an R squared of 0.66. And we've done this for other areas. It's usually between 0.6 and 0.7. So, but we've improved upon this a little bit further. We've done 2 different projects here. One is in our group, one was in Tracy Holloway's group with Elliot Kim. In our group, Omar Nawaz has been working on a land use regression to estimate urban, well actually NO2 surface concentrations at approximately 1 kilometer spatial resolution at the monthly timescales. The R squared is about 0.72. It's a little bit low. It's maybe a little bit lower than you might expect because it's at the monthly timescale. If you did this annually, it'd be a little bit higher. But we can see all very nice spatial, high resolution snapshots. And this, I don't have time to show what TROPOMI looks in these regions, but it looks very similar to what we're seeing at the surface. So we're purposefully only using a limited number of variables included in both of these methods, and I'll talk about Elliot's in a second. But we really want TROPOMI to drive these estimates and not other variables. Other variables can be helpful, and we want to include them when they are helpful, but we really want TROPOMI to be driving this. In Elliot Kim's work, which is under review right now, he's doing a regression with the Anscombe transform, and again, just 2 slightly different methods, both look relatively similar. But again, what I want to truly emphasize here is that TROPOMI NO2 is the driver of these surface concentration estimates. With using OMI in the past, that was not necessarily the case. So let me walk you through this. This is actually a pretty important table. This is showing that if we actually remove the satellite data from the land use regression product, we're seeing about a 29% decrease in that R squared. If we use TROPOMI, if we take OMI out of it, we're actually only reducing it by 6%. So this is just re-emphasizing how satellite data, and specifically TROPOMI data, is so important to estimating the surface concentrations. And the other variables are also important, but not as important as TROPOMI. Last but not least, I do want to highlight this paper that was discussed by Doug Boyer earlier today. I realize that some of you might not have attended that session, so I will highlight it again here. We were comparing this is not using satellite data at all, but it's highly relevant to this session. And this is where we're comparing models to the GCAS aircraft data, the measurements taken by Laura Judd and her team. And we're comparing the model source apportionment to the aircraft data, and we're trying to constrain the individual source sectors for NOx emissions. And we did this using a multiple linear regression model, and we found discrepancies in individual source sectors. And on-road emissions, which represent only about 19 to 20% in Houston, it's larger in other cities, most other cities in the US, we found that they needed to be increased by a factor of 1.6. So there was an NO2 or NOx underestimate in Houston. However, we simultaneously were able to find that shipping emissions were actually overestimated and needed to be decreased. So even though we saw an NO2 underestimate in the model, we were actually able to tease out that there might have been a shipping overestimate. And so we were able to pick out these individual source sectors. And one other thing is that in the model, the background NO2 needed to be increased, and there are a lot of reasons, hypotheses as to why that may be. And I won't get into that now. But last but not least, I do want to just highlight tempo data. Maybe my animation will work. Yes, sorry, Michael. This was just from a few days ago. It is a different day. This was a day when we actually saw some lightning knocks in the Florida Panhandle region. I filtered this in sort of my unique way, cloud fractions, and actually screened out negative values. Did a little bit better with the striping. But you can kind of see that lightning knocks coming from the clouds going over, and then the clouds sort of dissipate, whereas TROPOMI doesn't see that. And I'll show that in the next slide. It doesn't see, the clouds sort of dissipate in the afternoon. And so it's relatively obvious that this is coming from lightning knocks. Also, I want to highlight, look at the Dakotas. We can see some soil knocks probably originating in the mid to late afternoon there as the temperature is warm. So last but not least, the TROPOMI meeting. I want to just do a very quick intercomparison, TROPOMI and tempo. These look very similar on the identical color bars here. And it's just amazing at how similar these are. And I'm just really excited to use all the tempo data. With that, I guess we can open it for questions.
So we'll invite our panelists to come up to the front here, and we can open the floor for questions. Go ahead, Brad.
So has anyone started either in New York or California looking at what the air quality impact would be of a 100% electric vehicle fleet? Has anyone done those kind of, zero out on-road emissions?
There's been modeling of the entire action plan. Yeah, I think that's all on our website. But I can't answer you specifically.
Okay.
So we'll see reductions in tailpipe emissions, but there's still tire wear and the road emissions themselves.
Okay, thank you.
Okay, I see. Yeah. Great. Okay, thanks. And then
this question from the Zoom chat is from Zarosh Nayastani, and they say, thank you for interesting talks. Is there any general technique to remove or reduce aerosol shielding effects when retrieving column NO2 using TROPOMI over regions with high AOD? e.g. large wildfires?
Yeah. Aging wildfires, about the AOD, could,
I'm not the person.
Yeah, that's all by can somebody in Boulder answer that question?
Let's see. The OMI TROPOMI folks, you should be able to unmute if you want to.
The question is there any general technique to remove or reduce aerosol shielding effects when retrieving column NO2 using TROPOMI over regions with high AOD?
Okay, so it's about retrieval of NO2 with high AOD due to aerosols.
Yes.
Okay, well. Lock. Ah, good. Yeah, we have an expert here.
Yeah, so I'm Lok Lamsal. So if there is aerosol, it could have something similar effect as cloud. So cloud filtering might help there. So other technique would be to collocate aerosol information and NO2 data and then remove by yourself, by the user themselves. So that's another way of doing it.
Great, thank you so much. Yeah, I saw a hand back here. Thank you.
You're welcome.
Hello, this is Arlene Morales, Weld County Air Quality Policy Analyst in Northern Colorado. And one question, this is likely a research question, but the plot that was showed of, I think it was Connecticut ozone and how over time it's been decreasing and then it kind of has stalled in the delta of ozone over time. We're seeing that in the Western US as well, in Colorado. And I think last week I saw it for Arizona and other people in Utah and I forget what other states that they saw the same thing. So what is going on that is something else contributing to ozone? Are our control measures no longer working? It seems like this is happening across, well, I don't know, from my 3 points of data. But this is really, really curious, and I would like to know what is going on, or at least what are your theories?
Like, this is Michael from Connecticut. I guess a lot of us realize that we've reached the low-hanging fruit already, and everything just becomes more difficult. I mean, the electrification cars, if you could snap a finger and remove all the mobile source emissions, at least on road, you'd probably see a decline. But that's going to be the hardest thing. I mean, that's the major source right now. I don't know if anyone has any other ideas of what can be done about this.
Well, I can just back up. Over the years, I've asked people about that. Why are we seeing NO2 flatten out over time? And it's basically this concept of low-hanging fruit. We're doing, basically what's been done is what can be done with a reasonable amount of cost. And to make successive little incremental changes in NO2 reducing it is going to be more painful. It doesn't mean they can't be done. It's just going to take a while and it's going to be expensive.
I did want to add another thing too, because our modeler, Alex, I believe, did in New York, perhaps did the modeling of the whole home electrification to see if they, well, you know, all the residential homes and maybe apartments. And, you know, you have to displace the those emissions, well, to the power plants, of course, if you're going to have electric heat in every home with heat pumps. But so they did the modeling, and from what I could tell, it might decrease our ozone by 0.5 ppb. Now, modeling is not always that accurate, but that would be a big endeavor too, right? So we don't see anything too obvious. I guess that's my comment.
Yeah, just to say more explicitly, yeah, I mean, we really haven't seen NO2 dropped all that much between 2021 and now. Yeah, I just sort of expand on what they're saying is it's these sort of non-road sources. That's sort of the technical term that EPA uses, is these like construction sources and sources that are just not on roads, off-road sources. You could think about lawnmowers, and those they add up over time, especially in an urban area. So there are a lot of other sources. It was power plants. In my opinion, it sort of was light duty vehicles, and this is not more an opinion. I think light duty vehicles have been relatively good. I think it's sort of the heavy duty diesel, both on road, off road, non road, that I think is kind of the next sector to go at. And airports, yes.
Great. We have a comment in the chat from Pat Reddy in Colorado, I assume. It says, thank you for your presentations. Any thoughts about using satellite NO2 as a surrogate for tracking carbon emissions reductions? So Dan, do you want to?
Yeah, so we've done a little bit of work on that. We have a paper that's in prep or just about to be submitted. I'm doing synergies between OCO3 and TROPOMI, NO2. And so ideally you want to be using both satellite instruments for both types of measurements, but TROPOMI is really helpful in getting where that plume actually is to therefore isolate which OCO3 measurements to actually use. For those not familiar, maybe I should give an intro to OCO3. OCO3 is on the International Space Station. It's taking snapshots, or SAMs, I don't know, what's it stand for? Spatial area mapping, I think, of just of urban areas and a few others. And then those can be combined with NO2 to try and isolate where the CO2 is coming from in the cities. But then also you can just use ratios to estimate CO2 from the NOx emissions, and I've done that in the past too. But ideally, you want to be using some type of measurements for both.
Okay,
Maybe
great,
we
thanks.
could add something here from
Yes, please
Boulder.
go ahead, Pieternel. Yes.
Yeah, so we had a whole session on this capability from satellite to measure as well NO2 as CO2 as methane, and apart from OCO, there will be new measurements from Europe with CO2M, which is combined with NO2. Also, Japan will have HAQAST with an NO2 sensor added to it. And there are some small missions, small set missions. A new one is TENCO, which uses that combination. So I think there will be a lot in the future, which will be there, and where you can use that combination of NO2 and CO2 to get a better handle on fossil fuels.
Wonderful, thank you. I think I'm going to take prerogative as session chair and just ask a question here while we have the TROPOMI-OMI folks online here and our panel, and just ask about a more general question of kind of lessons learned from OMI, and then maybe in terms of thinking about, this amazing 20+ year record from OMI, what lessons there might be for the continuity of TROPOMI going forward. We already have several years, but of course it would be wonderful in terms of kind of continuing these kinds of trends that have been demonstrated for OMI to have the high spatial resolution of TROPOMI. And then of course, lessons generally for tempo and starting to think about geostationary. So a broad question, but I don't know, Paterno, while you have the mic, do you want to go first and then we'll pass in the room here? Oh, I think she. So yeah, Paterno, I was hoping to hear from you kind of lessons learned, or maybe Bryan, do you want to go first with OMI and then we'll bump to the room for TROPOMI?
Okay, so I won't answer your question exactly, but when you were asking it made me think of something. So again, I'm old and ugly at this point, and I have a lot of experience. So I'm thinking way back to 2005, 4 or 5, when the satellite was launched. And one important lesson I learned, especially for this audience, is at the time, a lot of the NASA people promoting OMI were overselling what OMI could do to the air quality community. And I think they did a real disservice, because they were saying, you can just throw away all your monitors. You don't need those anymore. We're going to do it all for you. That's not how it worked. I think that was a mistake. So I think a lesson learned for TEMPO and TROPOMI and all these other satellites is don't oversell your data. Work with the stakeholders. make them understand what they can and can't do with the satellite data. And make that clear, because I've seen quite a few stakeholders in the past really misuse the data, unfortunately. And it's because satellite data are complicated. It's not easy to use them. So really do work closely with your scientists, and I think you'll be better off for it. So that's a lesson learned. Don't oversell it from the satellite perspective, and for the stakeholders, don't be shy. Ask us for advice on how to best use the data.
Okay, so let's go to the OMI TROPOMI meeting and hear perspectives from there.
Yes, this is Pepijn Veefkind. Can you hear me?
Yes. Yes.
Okay. One of the, I think, lessons learned from my OMI and TROPOMI experience is that it's not the satellite data alone that is used by the broader community. You really have to integrate it within a modeling environment. So in Europe, we have the Copernicus program where we have a big system that assimilates different kind of inputs, including our satellite data as well as ground-based monitors, and produces forecasts as well as reanalysis of air quality at both the global scale as well as the regional scale over Europe. And I think that system is a very important component next to our observations.
Great, thank you. Any other perspectives in the room in Colorado?
Well, I might add to this that I think indeed that the combination of satellite ground-based and where needed also aircraft data is really what we need for fully understanding what we have for air pollution on the surface. I actually have a question on that for Dan Goldberg. Could I ask that question?
Of course.
Because I was interested in his last slide where he compared OMI and TROPOMI in relation to surface NO2, and TROPOMI is doing better on that, much better than OMI. My question would be, how do you think we can still improve on that relation? And will Tempo have more information because you have several measurements a day instead of only once? And could we use that information for that? What are your thoughts about that?
Yes. Yeah, so the slide you were specifically, or table you're specifically referring to, I mean, they were two different methods to estimate the surface concentrations. OMI was doing it a slightly different way than TROPOMI, so it wasn't exactly apples to apples. But with that said, I mean, TROPOMI does capture a lot of the urban spatial heterogeneities better than OMI. And so, that's why we want to be relying on TROPOMI, not as much on OMI. Personally, I'm a little bit hesitant to just throw 50 variables into a model. Even if it says it's not overfitting, in my opinion, it is overfitting. When you're putting in variables that might be correlated but have no geophysical reason to be in there. And so really we're trying to minimize the number of variables included in the model, and that comes with sometimes a lower R-squared value, but intuitively it looks a little bit better. At least what I would expect it to look like, especially in more rural areas. For Tempo, yeah, I mean, yes, I'm hoping that it can be used. I've only been working with the data for a few weeks now, so I'm really excited to be using that. But as Arlene and Tracy showed this morning in their group's work, there's gonna be a lot to work to be done to understand, especially what's going on in the morning and the evening to convert that column to a surface. But in the afternoon, it seems like there's pretty strong correlation between the surface. I think there's several people presented on that today, that if you just look at that snapshot in the early afternoon, there's pretty strong correlation. So there's maybe less that needs to be done in the early afternoon. I don't know if that specifically answers the question, but.
Great, that's interesting.
Thanks. I guess before we move on to our next question, is there any other comments or questions from the TROPOMI-OMI meeting?
Yeah, there is one.
Great.
I just wanted to thank Bryan for his comment about overselling. I want to, this is Barry Leffer, just in case you don't recognize my voice. We're really excited that the tempo data is public, but right now it's NO2 and formaldehyde and total column ozone, and I just want the folks in Boston in Cambridge to understand that the ozone profile is not ready, and I really don't want to oversell that product. It's really a research product, and it's not really measuring the surface ozone. There's a large averaging kernel there that is it's getting the lower 0 to 6 kilometers or so. So it's going to be an interesting piece of information, but it's not going to replace those surface ozone monitors.
Great, thank you, Barry.
I think these were the comments from this room. So no further comments here from Boulder at the moment. Thank you.
Okay. Okay, great. Thank you. So we're going to go. I think Kara had a question in the room. Yeah.
My question is pretty specific, so I think I'll just.
Okay. Okay. I think. Did we have a question in the back? Great, Kevin. Thank you.
I was really impressed by Bryan raising the point of OMI's contribution to stratospheric ozone. I think he was right in saying that actually led to informing policy decisions, while a lot of the OMI work, which is brilliant, let us track the progress of changes, but didn't really drive the decision making. And I wonder if either Ellen or maybe Barry in the other meeting could comment a little bit as we look forward to tempo. What are the things that might be able to drive decisions in addition to just tracking progress, which is what they're typically been used for?
That's for me. Okay, driving decisions and tracking progress. So
just driving decisions.
Just driving decisions. Okay. Well, a lot of what we can do is incentivize, help people make the better decision, right? And that's whether that's through a rebate or a tax credit or whatever. Looking at local community sources, depending on what it is, the funding for these incentives are to be focused on disadvantaged communities. At least 40% of the funds for incentives should be in disadvantaged communities. And so if we can identify a source and that may be a small EGU, it may be a warehouse that should be electrified or something along those lines, or rail spur, or thinking about sources like that could help drive decisions with incentives. We're not limited by being a regulatory organization because we're not one. And so we like to do a lot of pilots and try and find out what is actually practical. So for sure, that could help with decision-making. Some of the modeling work that has been done and the follow-up epidemiology in New York City with New York City Health, really looking at where, I gave an example of sulfur dioxide. That heavy number 6 oil was concentrated in certain neighborhoods. And so repowering that is not simple, even if it's just going to number 2, you have to replace some of the boiler components, but that can have a dramatic effect in lowering PM and having a real impact at the local level. So I would say that's the kind of thing we look for. We have some low-cost sensor work going on in New York City now, and we want to be able to look for local sources off of that. They'll use conditional probability function analysis, and we don't know what we'll find yet. We're not finished just doing the monitoring, but we'll get to the analysis phase. I hope that helps answer the question.
Yeah,
go ahead, Barry.
Dan, I'll jump in real quick and then let you go. Totally agree. one of the real valuable things about Tempo is discovering new sources. You know, we have the great EPA monitoring network, but Tempo can tell folks, maybe we should put a monitor in this neighborhood. There's a source, or just low-cost sensors, or even a mobile monitoring device could go and find a source that we need to add to the inventory. And again, and EJ would be another one. So yeah, I think you all did a great job answering that question.
Yeah, I'll just build upon both said, but I guess a little bit more explicitly what Barry just said is that having measurements does lead to action. I sort of little bit disagree with the premise of the question, is that because if you do have a measurement anywhere, there has been a study. Let me take a step back now. There is this study, I think it was done in Australia, but it was using US embassy data. They said that when they put a PM 2.5 monitor in a new location, the PM 2.5 came down a few years later. So once you have a measurement in a location, it spurs the local community, gives them awareness, and then they'll vouch for action. So yeah, just the satellite data, I like oversampled data because you can really sort of pinpoint the hotspots in any individual region, and you give that to the local community. Maybe the state agencies might not be super thrilled with that, but you could just give an oversampled image of a certain region and say, well, your neighborhood has the highest NO2. What would you like to do about that? And there'll be some community meetings about that probably. So I think that the spatial images do a lot to help drive people's awareness that can then drive political pressure.
I would say, looking at electrification of school buses, we are going statewide with electric school buses. We turn over our school buses every 10 years, sorry, which is a short lifetime compared to most states. And so bus depots where there'd be a lot of vehicles idling, I don't know whether you can see that with Tempo, but that's the type of thing, if that pops up, we might be able to do something and actually get to mitigation. And it's great, my program studies things, but all my colleagues who are deploying technologies, they're actually doing the mitigation. And so when I get to work with them, I get very excited that I can actually have an impact.
Great. We have an online a question in the chat from Jiachan Zhang, who says, thanks for the very informative presentations. I have a question for Dan regarding how to ensure a fair comparison between column NOx concentrations and bottom-up emissions inventories. Could you share your thoughts on using a chemical transport model versus your approach?
Yeah, so we've done both. One thing when we do compare with chemical transport models, well, first you need to make sure you're doing the averaging kernel, but actually, so almost of equal importance is to account for biases in urban areas. Oftentimes, or the TROPOMI team, they have the validation document. They show that there's a pretty substantial bias of the TROPOMI in urban areas. And so it's really important to take that into account when you're doing this model intercomparison between TROPOMI and any models. But it can be done. It's just different ways. It's sort of going to, you have one approach doing one way, one approach doing a different way. Hopefully they're in agreement. If they're not in agreement, then you find out why they're not in agreement. So both can be okay and accurate ways to do it, or valid ways to do it. But sometimes people don't have access to chemical transport models, so that's obviously a limiting factor.
Great, thank you so much. So we have like a minute left, but I wanted to open the floor back to Boulder and see if there's any final thoughts or questions. Not seeing any. Wow, it's even worse over Zoom than like being in the room. Any burning questions here in the room? Okay, actually we have one more, so we'll take that and then
yeah, this is Xiaohua Pan from NASA Goddard. So this question is really asked for user. So for this community, it's air quality and health community, I think that they might be more concerned on the surface NO2 and ozone. So do you have any advice to how to use like satellite troposphere NO2 to indicate the surface NO2?
Yeah, well, we're developing products to do that, hopefully globally, but in the near term, we have some US-centric products that convert that satellite data into surface concentrations, and we're working on that. Is that the question? Yeah, but I don't know, Brett, somebody else want to comment on this? But yeah, sometimes there are high correlations, sometimes there aren't. Jeff Geddes kind of showed that today. So it gets complicated, especially on a day-to-day basis. But annual average, there's higher correlation between the surface and the column.
Daniel wants to say something.
Comments here from the room in Boulder from Daniel Jacob.
Hi, thanks for your presentation. A question. Do you see the need to take into account the background free tropospheric NO2 when trying to interpret the observations?
Yes.
Yes. The answer is definitely yes. In a lot of my work in the prior, I do that. In a lot of the plots I showed today, I just zoom in on the urban areas. But yeah, I try for publications, I definitely take account for the background, at least me personally. It is important. It definitely is important.
So are we affected then by uncertainty in our understanding of that background in order to be able to relate the column observations to surface concentrations, for example?
Yeah, it sort of depends on what your goal is. And I'll sort of go back to what I started off my talk with, which is if you want to get a highly accurate product, then you have to do everything possible to do that. But if you're just trying to get a surface concentration to an area that's never had an estimate of a surface concentration before, then you maybe can do something quicker and get something out the door quicker. So it just depends on what your audience is. If it's a scientific publication, then you have to do some things more rigorous. If you're just trying to get a quick estimate to a stakeholder, then maybe you can do something quicker.
All right, so I think it's important to keep in mind the application and understand which uncertainties are most important to be taking into account. And with that, I think we have to close out our session. Thank you so much to everyone in Boulder for joining us and for being part of the dialogue.
Yeah, thank you. It was very interesting first experiment. Maybe we should do it more often. Thank you.
That sounds great.
Yeah, if you want to turn around and wave at the camera.
Oh. Great. Let's thank our speakers and everyone in Boulder.